Hello again, so this is question 14. For question 14, we have to draw a diagram of an on-pop-based first-order high-pass filter with a resistor R1, feedback resistor R2, and a capacitor C. So let's start drawing this circuit. So A, a first-order high-pass would have a resistor R1, a capacitor in series, and then it connects to the inverting input of the amplifier. We can ground the non-inverting input, and then here we have our feedback resistor R2. So this is R2, this is C, this is R1. This is V out, this is V input. Okay, so that's the circuit. Now for part B, we need to derive an expression. So for an expression, again we are going to represent the capacitor using a reactance, so that's 1 over J omega C, right? Remember that for an ideal op amp, V plus is equals to V minus. And in this case, because it's grounded here, they are both 0 volts. And because I plus equals to I minus equals to 0, so there is no current entering here or there, we can apply KCL at this node here. And then we get, so V minus minus VI divided by R1 plus 1 over J omega C plus V minus minus V out divided by R2, that's equals to 0. So remember that this one here is 0 volts, this one here is 0 volts. So we can simplify this equation as, minus VI over R1 plus 1 over J omega C plus minus V out divided by R2, which implies that if we isolate minus V out, that's equals to 0, and then that implies that V out over VI is equals to minus R2 divided by R1 times 1 plus 1 over J omega C R1. So that's the voltage transfer function, so this is equals to H of J omega. That's the voltage transfer function. Okay. Now for part C, we have to define an expression for the DC gain, and for part D, an expression for the 3 dB voltage, 3 dB for the 3 dB frequency, right? So B, let's go with C. Okay, so C, let's call it DC gain. For the DC gain, we have to calculate the magnitude of the voltage transfer function. So if we look at there, that means that the magnitude of the voltage transfer function is equals to R2 divided by R1 times 1 over so just to calculate the magnitude, let's simplify that equation by multiplying everything by J omega C. Okay, so if we multiply everything by J omega C, we get, take off the magnitude here. So this is a second way to write the same voltage transfer function, J omega C R2 divided by 1 plus J omega C R1. That's the same equation that we got up here. It's just that I'm multiplying by, so I'm multiplying this by J omega C and down here by J omega C. Okay, so then this J omega C R1 cancels out. this one becomes 1, and this second part here becomes j omega cr1, and up there minus j, so it's minus j omega c r2. Now if we then take the magnitude of this, okay, magnitude of j omega, this is equals to, so for this particular case, because for the numerator, because you only have like the imaginary part of the complex number, that it's equals to omega r2c, right, divided by the square root of the real part, 1, plus the imaginary part, omega c r1 squared. And the DC gain is when omega is equals to 0, right? So if we substitute omega here, here, and there by 0, this gives us that our gain at DC, because we have omega on the numerator, so h of 0, the magnitude, is equals to 0, right? So it's multiplying here omega, so if omega is 0, the gain is 0, right? And here is just going to be like square root of 1, because this term here will 0 out, right? So it's just 0, which means in dB, the log 10 of 0, it's undefined, so it's minus, we say that it's minus infinite here, right? So those are the gains at DC. Now for part D, we have to calculate the 3 dB frequency. So for part D, 3 dB frequency. Okay. And for the 3 dB frequency, we can still keep the same representation that we had before for the h of j omega, right? And this is equals to r2 over r1, right? Times 1 over 1 plus 1 over j omega c r1, right? So if we take this in the magnitude of this, then we get h of j omega equals to r2 over r1. So this is a constant gain, call it a DC gain, but it's just constant, right? So it's a DC gain. And then times, so the magnitude is 1 for the numerator, and square root, go a little bit to the left, to the right, 1 squared plus 1 over omega c r1 squared, right? So that's the equation that we have. Now for a 3 dB frequency, so what's the frequency that we have at 3 dB, right? So at high frequency, we have this, sorry, this is not the 3 dB frequency, this is the high frequency gain. So for the high frequency gain, we say that we are at 3 dB below the high frequency gain if this term here is equals to 1 over square root of 2, right? So for a 3 dB, remember the power is halved, so it means that the amplitude, the voltage, should be 1 over square root of 2. So 1 over square root of 2 should be equals to 1 over square root of 1 squared plus 1 over omega c r1 squared. Okay, so why are we ignoring this term here, right? Because this is the frequency. You see on the body plot that we have something that looks like this. So this gain here this value here is defined by 20 log 10 of R2 over R1. So these stay constant for very high frequencies. And then the 3 dB frequency is exactly when we are 3 dB below this high frequency gain. So it should be something here 3 dB below that. And who decreases the gain? This term here. It influences the gain at low frequencies, right? So because if then it becomes very low here, this term of 1 over omega CR, it will basically decrease our gain here, and then we are reaching this part here. So if we take this R2 over R1 and then multiply that by this term here exactly at 1 over square root of 2, then we get the 3 dB frequency. So this means that this 2 here should be equals to this term here, which gives us 2 equals to 1 plus 1 over omega C R1 squared, right? And this implies that omega is equals to 1 over C R1. Okay, so if we let's just so if we pass this one to this side, becomes 1 equals to 1 over omega C R1 squared, and this is the same as, so if we put the omega squared up there, multiplying the 1, this is omega squared equals to 1 over CR1 squared. If we take the square root both sides, this is 1 over omega CR1, which is the equation that I derived here. Okay, so this is the equation for the 3 dB frequency. Okay, so it's 1 over CR1. So this was part D of the fourth question. Now for part E, we have a design. So if I go up there again on the statement, so we have to design the component. So let's see, this is part E, the design, right? So for the design, we have R2 equals to 10K, so this is given. We already know the value of R2. We want a high frequency. Yeah, so remember, this is not the, so this is not I told you before that was like a DC frequency R2 over R1. That's the high frequency gain. I just thought about the other case, but this one is the high frequency gain. So we want that to be 60 dB. So a high frequency gain of 60 dB and a 3 dB frequency. So I know I shouldn't call it omega again. So it's just 3 dB frequency, right? Equals to 10 kilohertz. So those are the constraints of our design. So R2 we already know, and because we know that the high frequency gain, so the high frequency gain as omega, it's very high, means that H of J omega is equals to R2 over R1. Okay, so if you want a 60 dB, this means that the linear gain is equals 10 to the 60 divided by 20, which is 1000 volt per volt. This means that our R1 is equals to R2, 10K, divided by 1000. Which means that our R1 is equals to 10. So we got R1, we already know R2. Now from the 3 dB frequency gain, we can calculate the capacitor value, right? So for the capacitor value, we know that 2 pi times that 10 kilohertz is equals to 1 over C times R1, right? This implies that C is equals to 1 over 2 pi times 10k times 10, which is our 1, and this gives us 1.59 microfarads. Right, so this is the capacitance. So we are done with the design. Now for part F, we have to define an input impedance. Okay, so for the input impedance, let me go down here. It's called part F, input impedance. So if you remember, we had our circuit like this. And then our input impedance, if you remember, this is 0 volts because we are grounded here. This is VI. We can calculate the current I1 here, right? And then our input impedance, in this case, Zn, is equals to VI divided by I1. And I1 in this case is just VI divided by R plus 1 over J omega C, right? Because they're in series, this is 0, the current I1 is just using Ohm's law. So if we substitute this one here in this equation, we get that the input impedance is equals to R plus 1 over J omega C, which in our case is equals to 10 minus J 5 ohms. So if we plug in the values of R1 here, so this is R1, R1, C, R2. So if we plug in the values of R1 as 10 and so we need to define the input frequency at 20 kilohertz. So at 20 kilohertz, input impedance is just 10. So this one is 2 pi times 20k hertz, and then this C here is 1.59 microfarad. This gives us 10 minus J5. Okay, and part G is the unity gain. So part G, unity gain. So we again manipulate the magnitude. So remember that the magnitude 8 of J omega is equals to omega R2C divided by square root of 1 plus omega R1C squared. So if we take that equals to 1 equals to omega R2C divided by square root of 1 plus omega R1C squared. If we square both sides, it gives us 1 equals to omega squared R2 squared C squared divided by 1 plus omega squared R1 squared C squared. And then if we manipulate this again, we get that omega is equals to 1 over square root of R2 squared minus R1 squared times C squared. Okay, which in our case gives us omega of 62.83 radians per second and a frequency of 10 hertz. Angular frequency of 62.83 radians per second and a frequency of 10 hertz. Okay, and for the last part, we just have to plot the Bode plot. So we'll call it H. Now for the Bode plot, the magnitude, so we can represent the voltage transfer function H of J omega, which was J omega C R2 divided by 1 plus j omega c r1. If we pass that to polar form, this is minus, right? So we have 1 with 180 degrees, right? Because of this is minus 1j, okay, times the magnitude of j omega cr2, which is omega cr2, with an angle of 90 degrees because of the j, right? Divided by the magnitude of the denominator, which is 1 plus omega cr1 squared, and the angle here is the arctangent of the imaginary part, omega cr1, divided by the real part, which is 1. So this is the polar form. Now if we extract the magnitude, we get the same equation that we had before. So this is the linear, okay, which is 1 times omega cr2, so it's omega cr2, divided by the square root of 1 squared plus, which is just 1, divided by omega cr1 squared. So this is the magnitude. And now for the phase, we just apply the same rule for phasors. So if they are multiplying, basically means that we take 180 plus 90 minus the arctangent of omega cr1 divided by 1, just omega cr1. Okay, so this gives us a phase that is 270 degrees minus arctangent of omega cr1. Okay, and again we have like a beautiful plot on the solution manual, but if we want to plot these equations here, we can plot the magnitude. So I'll just write it down here, the axis. So this is the magnitude, and now for the body plot, we plot the magnitude in dB. And remember that for dB, we just take this number here, take the log 10 of that and multiply by 20. Okay, so again, I will go from, so I call this exactly here, it's not 0, it's 10 to the 1, this is 10 to the 2, 3, 4, 5, 6, 7. To the 4, 10 to the 3, 10 to the 2, and exactly here it's 10 to the 1. So the origin here is 10 to the 1. So we know that we have specified that for a high frequency gain we would expect to have 60 dB, okay? And we know that the 3 dB frequency is exactly at 10 kilohertz, right? So let's see, 10 kilohertz. 10 kilohertz in corresponds to roughly 62 kiloradians per second. So 62 kilo, so it's around here. And let me say we have 60, sorry. Just put this axis a little bit to the right. $60, 40, 20, and here we could say minus 20. So around here, 10 to the 5, we have 57, right? Because that's the minus 3 dB. Now for 10 times that, so here's omega 1 decade before and 2 decades before, we are mostly at 60. Okay, so here and there. Now 1 decade earlier, so if we were at 60 here, so we are here at 57. Basically 1 decade before that it's 40, so we are decreasing 20 dB per decade, minus 3 dB, so we are around here, right? 1 decade earlier we decrease another 20 dB per decade, so it's 20 minus 3 dB, so it's around here. And then 1 decade earlier here we decrease another 20 dB minus 3 dB, so this we couldn't say that it's, let me just zoom in here, this is minus 3 dB, so we are around here. Okay, and then if we plot this so we have our unity gain at around 10 Hertz, right? So this is close to, right here it's 62 radians per second, which corresponds to mostly the 0 dB, right? And for the phase, so let me plot the phase here. Again, 10 to the 2, 3, 4, 5, 6, 7. Remember that we start here at, well, we start at 270, right? And then if we are exactly at the 3 dB frequency, we are, which is frequency here, omega equals to 1 over CR1, we decrease by 45 degrees, which gives us half here, that is 225. And then exactly here we have 180 degrees. So let me write this down. So 10 to the 2, 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6, 10 to the 7. So exactly around this frequency here, we are at this point. This is roughly the plot, right? We can precisely calculate for the points of interest, like 10 to the 2, 10 to the 3, 4, 5, 6, 7, and then we can specify a precise plot, so we can see that precise plot on at CUlearn in this solution sheet that we have. But this is roughly what we have. So exactly here at around this frequency, we have this arctangent of 1, so it's 270 minus 45, right? Around here, 10 to the 4, we have something that it's 250 to 60 something here, so it's around this region. And then here we start to approach 270 degrees, right here. And then the same here, so for 10 to the 15, we have something here around 216, 218, 218. 10 to the 6, we are more close to 180, and eventually here 10 to the 7, and for higher frequencies we keep constant at 180 degrees. So if we draw the phase here, that's the phase we observe, right? So this is basically the Bode plot, okay? So there might be like some kind of a little bit of shift on the values that I got here, but basically that's the overall behavior that you observe. So if you want like precise values, you just have to plug in the values of CR2, R1 that we design along with omega, and then you can basically specify each one of those points precisely, okay? But if you look at this circuit here, basically this behavior, we observe that this is a high pass filter, right? Because for high frequencies here, we keep a constant gain of 60 dB. and once we reduce the frequency around here, we start to attenuate. So this plot here, it basically decreases by, or yeah, so if we going this way, it decreases 20 dB per decade. Okay, but if you look at from this side here, it's increasing, like in this direction, it's increasing by 20 dB per decade. Okay, so that's it for this problem.